You already know how Mars is supposed to kill you. You have seen the version where the radiation gets you, where the cold gets you, the kind that drops past 100 degrees below 0 Fahrenheit on an ordinary night, where the air, if you can even call it air, is 95% carbon dioxide and thinner than the summit of Everest, and one failed seal on a helmet ends everything in under a minute. You have seen the dust storms that swallow the whole planet for weeks at a time. These are the deaths we put in the films. They are loud, and they are fast, and they are honest about what they are. None of them is the thing most likely to kill the first people who try to live there. The thing most likely to kill them is assault. It is already on the ground. On every part of the ground we have ever tested. It sits in the soil at roughly 0.5% to 1% by weight, which sounds like nothing until you learn what it does to a human body in amounts far smaller than that. It has no smell. It has no color you would notice on a red planet. It is fine enough that the wind has carried it into every corner of the world, and fine enough that once it is in your lungs cannot get it back out. It is called perchlorate. This is a video about perchlorate, and about all the quiet ways a planet can be lethal without ever raising its voice. We found it almost by accident. In 2008, a small NASA lander named Phoenix scooped up a cup of dirt near the Martian North Pole, mixed it into water it had carried all the way from Earth, and measured what dissolved. The answer came back wrong in a way nobody had planned for. The soil was laced with a chlorine compound that, here on Earth, we keep behind warning labels and pack into rocket fuel. And the missions that came after did not walk the finding back. The Curiosity rover found the same chemical signature almost everywhere it drilled. What emerged was not a contaminated patch of ground, it was a contaminated planet. If you enjoy these journeys into the strange and the cosmic, hit subscribe and settle in. This is a long one, and it is meant to be heard slowly. Here is what makes it worse than the killers we fear out loud. The loud ones we can engineer against. We can shield a habitat, pressurize a suit, wait out a storm behind a wall. But this one does not stay outside the wall. It rides in on the dust that clings to everything you touch. It dissolves into any water you pull from the ground, and it works its way into the food and the air and the blood on a timescale slow enough that the first crew might not understand what is happening to them until the damage is already finished. And the strangest part is the water. The simplest plan for staying alive on Mars is to melt its buried ice and drink it. We will get to the exact number that breaks that plan. The point where a single day's worth of Martian water could carry several times over the dose that has already killed people here on Earth, and why no filter light enough to fly there solves it cleanly. Before we reach that number, you should know how seriously the danger of Mars has already been taken. The people who plan these missions are not dreamers. They are engineers, and engineers have been working on the problem of keeping a human alive on that planet for the better part of a century. By the time Perchlorate enters the story, there is already a thick stack of paper devoted to every other way the planet might kill you, and almost all of it ends in the same confident place. Solvable. Hard, but solvable. The first real blueprint came from Wernher von Braun. In 1948, before any human being had ridden a rocket out of the atmosphere, the engineer who would later build the Saturn V that carried men to the moon sat down and wrote a technical study called Das Mars Project, the Mars Project. He imagined a fleet of 10 ships assembled piece by piece in Earth orbit, carrying a crew of 70 across the void on a journey measured in years. The arithmetic was rough and the scale was almost comic. 10 ships of nearly 4,000 tons apiece, tens of thousands of tons of vehicle for a single expedition, but the document did something nobody had done before. It treated a trip to another world not as a dream, but as an engineering problem with real numbers bolted to it. And the moment you treat survival as an engineering problem, you begin building a list of everything that wants you dead. That list has been refined for 70 years. Most people could recite the top of it without stopping to think. Start with the cold. The average temperature on the surface of Mars sits around -80 degrees Fahrenheit, about as cold as the lowest temperature ever recorded in the United States. At the poles in winter, it falls past -190. Even at the equator, a pleasant afternoon that climbs to near freezing will plunge back below -100 once the thin air lets the day's heat escape after sundown. There is almost no atmosphere to hold warmth in place. The ground gives up its heat to the black sky every single night, and it does this relentlessly on a planet where the nearest repair part is 7 months away. The swing alone is punishing. A single Martian day can carry you through a temperature range wider than almost anything a human body or a piece of machinery ever meets on Earth. From something nearly mild at noon to a deep freeze by night, over and over, every day the crew is there. Metal fatigues under that cycle. Seals harden and crack. A spacesuit has to work as a furnace and an icebox in the same afternoon, holding a person warm against the cold while shedding the heat of their own effort. And it has to manage that while the dust grinds at every joint. The cold is not a single number to engineer against. It is a daily tide that never stops pulling at everything you build. Then the airs, which is barely there at all. The Martian atmosphere is about 95% carbon dioxide, and the pressure at the surface is roughly 0.6% of what you are breathing right now. To put that in a body you can feel, the air on the summit of Mount Everest, where climbers collapse without bottled oxygen, is more than 50 times thicker than the air at the Martian surface. Step outside without a pressurized suit, and the problem is not only that there is nothing to breathe, it is that the pressure is so low, the water in your own blood and tissues begins to boil at body temperature. There is a name for that line. Engineers call it the Armstrong limit, the altitude at which the air pressure drops so low that water turns to vapor at the temperature of a living human body, around 98 degrees Fahrenheit. On Earth, that line sits at roughly 60,000 feet, far higher than any airliner carries passengers, a place no unprotected person has ever survived. The entire surface of Mars lies above it. The whole planet, top to bottom, sits in the killing zone where exposed flesh effervesces like an opened bottle. You would have somewhere between 1 and 2 minutes of useful consciousness, and then the planet would simply switch you off. Then the distance, which is its own kind of hazard. Mars and Earth swing between roughly 34 million miles apart at their closest and more than 250 million at their farthest, and you do not get to choose the easy number. A crewed mission flies a long looping path that takes about 7 months one way. The standard plan keeps a crew on the surface for around 500 days, waiting for the planets to line up again before another 7-month flight home. 2.5 years, give or take, with no way to quit early. And the distance does something quieter than that too. A radio signal takes between 3 and 22 minutes to cross the gap, which means a cry for help, and the first word of any answer can be separated by as much as 44 minutes. There is no mission control in the moment. There is only the crew and whatever they brought with them. Which brings the list to radiation. We have an actual measurement for this one, and it is not a guess. When NASA flew the Curiosity rover to Mars in 2011, it carried an instrument called the Radiation Assessment Detector, RAD for short, switched on for the whole cruise. The numbers it sent back, published by Donald Hassler and Carrie Zeitlin of the Southwest Research Institute in the journal Science in 2013, were sobering. During the flight, the detector absorbed about 1.8 thousandths of a sievert of radiation every single day. The lead author of the study described it plainly. It was, he said, like getting a full-body CT scan once every 5 or 6 days for months on end. Add the round trip together and a crew picks up roughly 2/3 of a sievert just in transit. Spend the surface time on top of that and the total creeps toward a full sievert, an exposure linked to a 5% rise in the lifetime odds of dying from cancer. NASA's own career limit for an astronaut is set at a 3% increase. The math, read honestly, says a single Mars mission could push a crew past the line the agency draws for an entire working life. And then there are the storms. Mars runs dust storms unlike anything on Earth. Most are regional and seasonal, but roughly every 3 Martian years, which works out to about 5.5 of ours, the storms grow until they wrap the entire planet in a haze that can last for weeks. One of those global storms is what finally killed the Opportunity rover in 2018. The little machine had been built for a 90-day mission and had somehow survived nearly 15 years, and then the sky went dark, its solar panels starved, and it never woke up. A storm that can smother a hardened spacecraft is not a small thing to plan a human settlement around. Look closely at what that storm actually did, because it is a small parable of the whole problem. Opportunity did not break. Nothing on it failed. The storm simply threw so much dust into the sky that the sunlight feeding the rover's panels dwindled toward nothing, and the machine, unable to gather power, slipped into a long sleep it never rose from. The dust did not have to destroy it. It only had to stand between the rover and the light it lived on for long enough. A human settlement would run on that same sunlight, caught by those same kinds of panels, and the storms that ended Opportunity would, at the worst possible moment, dim the power that drives the heaters and the air and the water purifiers a crew cannot survive without. So that is the list. Cold that never relents, air that boils your blood, a distance that strands you, radiation that counts down your cells, and storms that can blot out the sun. It is a genuinely terrifying inventory. And here is the part that matters for everything that follows. For every single item on it, the people who plan these missions have an answer written down. The answer that changed the conversation belongs to Robert Zubrin. In 1990, Zubrin and a fellow engineer named David Baker, both at the aerospace company Martin Marietta, proposed a plan they called Mars Direct. 6 years later, Zubrin laid it out for the public in a book titled The Case for Mars, and his core idea was almost stubborn in its simplicity. Stop trying to carry everything from Earth. Live off the land instead. The technical name for this is in situ resource utilization, and the principle is that a planet, even a hostile one, is made of things you can use. The clearest example of that principle is a chemical trick called the Sabatier reaction, worked out by a French chemist back in the 1890s. Feed it carbon dioxide and a little hydrogen, add heat and a catalyst, and it hands you back methane and water. Mars has an atmosphere that is almost pure carbon dioxide, which means a crew could in principle land on the planet and begin manufacturing their own rocket fuel and their own drinking water out of the air around them, rather than hauling every drop across the solar system. The return ticket in Zubrin's vision gets made on arrival. It is an elegant idea, And it reframed Mars from an impossible destination into a place you could actually supply. That principle is no longer theoretical. In February of 2021, NASA landed the Perseverance rover in Jezero Crater, carrying a toaster-sized instrument called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. That April, MOXIE pulled carbon dioxide from the Martian air, stripped the oxygen off it, and produced breathable gas on the surface of another planet for the first time in history. The amounts were tiny, a few grams an hour, roughly enough to keep a small dog breathing. But the point was never the quantity. The point was that it worked at all, that the air of Mars could be turned into something a lung could use. The principle of living off the land had stopped being an argument in a book and become a measurement on a planet. Everything else on the list got the same treatment. The cold and the radiation you handle by going to ground, piling Martian soil over your habitat, or tucking it into a lava tube, letting the planet's own dirt absorb the cosmic rays that would otherwise reach your cells. The thin air and the boiling blood problem you solve with pressure, the same way a submarine solves the crushing weight of the ocean by holding a bubble of safe conditions inside a hard shell. The water you bake out of buried ice or pull from the atmosphere. The distance and the storms you plan around with supplies and shelter and patience. By the time you finish reading the modern mission studies, NASA's design reference architecture, the private blueprints from companies promising cities of 1 million people, you come away with a strange and specific confidence. Every named threat has a countermeasure with a paragraph and a diagram beside it. And almost all of those countermeasures lean on the same quiet assumption. Look closely at the plans and you notice that the Martian soil is not treated as an enemy at all. It is treated as the answer. You shield your home with it. You melt water out of it. You pull oxygen from the air that the same dust hangs in. The boldest visions go further and imagine growing food directly in it. Greenhouses of crops rooted in Martian ground, a settlement slowly becoming self-sufficient on what the planet provides. In nearly every architecture ever drawn, the regolith, that fine red dust covering the entire world, is the resource that makes the whole thing possible. It is the floor you stand on, the roof you hide under, the well you drink from, and the field you farm, which is exactly why nobody circled it in red. The whole survival plan rests on the ground being something you can use, and the chemistry that makes the ground so useful, the salts that hold water, the compounds that can be cracked for oxygen, is the same chemistry that makes it lethal. The 0.5% we measured in that first scoop of Martian dirt is not a force you can shield against with more dirt. You cannot pressurize your way past it or wait it out behind a wall. It is not a storm or a temperature or a dose. It is a poison woven through the one material the entire mission depends on: touching, breathing, drinking, and growing food in. To understand how we learned that, we have to go back to the spacecraft that found it. A small lander near the North Pole in the northern summer of 2008, running a single experiment that nobody expected to matter. Phoenix was never meant to be the mission that rewrote how we think about living on Mars. It launched in August of 2007 on a modest budget, a single stationary lander instead of a roving one, aimed at a flat stretch of the far northern plains called Vastitas Borealis. Its scientific leader was Peter Smith of the University of Arizona, and the goal was almost gentle by the standards of the program. Phoenix would dig down to the water ice everyone suspected lay just under the surface at that latitude, and it would ask a simple question. Had this ground ever been the kind of place where life could get a foothold? 90 days, a robotic arm, a few ovens, and a small chemistry set. That was the whole ambition. It landed on the 25th of May, 2008, and the first images sent home showed something that looked oddly familiar. The ground was cracked into shallow polygons, the same pattern you see in permafrost on Earth, where ice in the soil freezes and thaws and pushes the surface into tiles. Within days, the robotic arm scraped away the top layer and exposed a hard, bright material underneath. A few sols later, watching it slowly vanish in the sunlight, the team confirmed it. The lander had found ice, exactly where it had hoped to. The mission was working. The instrument that would change everything was a box on the deck called Mecha, the microscopy, electrochemistry, and conductivity analyzer. Tucked inside it sat a piece of equipment called the Wet Chemistry Laboratory, led by Michael Hecht at the Jet Propulsion Laboratory and by Samuel Kounaves of Tufts University. The idea behind it was clever and very human. To find out what a soil is made of, you do what a gardener does. You drop it into water and see what dissolves. The wet lab carried 4 small cells, each one a kind of cup, each holding a wafer of purified water brought all the way from Earth. You stir in a pinch of Martian dirt, and then you lower in a bank of sensors, every one of them tuned to recognize a different dissolved substance, and you read off what the planet gives up into the water. In June of 2008, they ran the first sample, and one of the sensors came back wrong. The electrode that misbehaved had been designed to measure nitrate, a common and unremarkable soil ingredient. But its reading was far too high to make sense as nitrate alone. Something else in the soil was tripping it, some ion the team had not gone to Mars expecting to find in any quantity. As they worked through the chemistry, cross-checking one sensor against another, the answer resolved into a single compound, and it was not a comfortable one. The Martian soil was laced with perchlorate. Perchlorate. On Earth, this is not a substance you stumble across in clean dirt. It is an aggressive oxidizer, a molecule built around a chlorine atom packed with 4 oxygens, and we make industrial quantities of it on purpose for specific jobs. It is the oxidizer in solid rocket fuel, the thing that lets the boosters burn. It goes into road flares and fireworks, and the propellant that inflates a car's airbag in the instant of a crash. And when it leaks into groundwater near a factory or a military site, it becomes a regulated contaminant, the kind of thing health agencies track in drinking water at the level of a few parts per billion. The wet lab on Phoenix was reporting it in Martian soil at 4 to 0.6% by weight. To feel the gap, hold those 2 numbers side by side. On Earth, the state of California flags perchlorate in drinking water at around 6 parts per billion. Dissolve the salt out of Martian soil into the water a crew would actually drink, and the concentration can run into the millions of parts per billion. The planet's dirt is not a little contaminated by our standards. It is contaminated by a factor that has too many zeros to picture. The team did not take the reading on faith. They were cautious, almost reluctant about announcing it, because a single misbehaving sensor proves nothing. So they cross-checked the wet chemistry against another instrument entirely, an oven that bakes soil and reads the gases that come off. And they worked hard to rule out the obvious worry that the chemical had hitched a ride from Earth on the spacecraft itself. The signal held. Later analysis pointed to calcium and magnesium, perchlorate, as the likely forms, and the soil came back mildly alkaline, with a pH close to that of seawater. Michael Hecht put the caution plainly. The result was exciting, he said, but it had come from 2 teaspoons of soil, and the real question was whether those 2 teaspoons spoke for the rest of the planet. Within a few years, the answer would turn out to be yes. Here is the strange thing about how the discovery landed at the time. almost nobody talked about it as a danger to people. The conversation in 2008 was about microbes, not astronauts. Phoenix had been sent to judge whether its little patch of Mars could ever have hosted life, and the question on every scientist's mind was what perchlorate meant for that search. Some microbes on Earth happily eat perchlorate for energy, so maybe it was a food source. It pulls water out of thin air and can keep liquid brine stable in brutal cold, so maybe it helped water persist. Michael Hecht summed up the mood by saying the finding was neither good nor bad for life, just something that forced everyone to reassess. When a reporter asked Samuel Kounaves whether the stuff was toxic, he answered carefully that he would not use that word. They were not being evasive. They were astrobiologists looking at a soil chemistry result, and the human question, the one about what 0.5% of an oxidizer does to a body that has to live in it, simply was not the question on the table that week. There was even a small storm of speculation around the announcement. In the days before the team went public, leaked reports claimed the scientists were sitting on some bombshell about life on Mars, that the findings were so explosive, the White House had been briefed. Reporters chased the rumor hard enough that the team had to step in front of cameras and calm it down. The truth was quieter and, in its own way, stranger than the rumor. They were not hiding a discovery about Martian biology. They had found a poison spread across the planet, and they were describing it, accurately and a little blandly, as an interesting result. The danger to any future astronaut was not the headline. It was a footnote nobody had written yet, and then the discovery did something that good discoveries sometimes do. It reached backward in time and rewrote a 30-year-old mystery. In 1976, 2 Viking landers had set down on Mars, carrying the most ambitious life detection experiments ever flown. One of those experiments seemed to give a faint, positive signal. But another instrument, the one meant to find organic molecules, the carbon-based building blocks of life, came back almost empty. That contradiction haunted Mars science for a generation. How could a planet's soil contain no detectable organics at all, when meteorites should have been seeding it with carbon for billions of years? The Viking results were filed away as a puzzle nobody could quite close. Perchlorate closed it. In 2010, a team led by Rafael Navarro Gonzalez showed what happens when you heat Martian-type soil that contains perchlorate, which is exactly what Viking did inside its ovens. The perchlorate, an oxidizer, ignites and burns up any organic molecules in the sample before they can be detected, leaving behind a few chlorine-tagged fragments. And those chlorinated fragments were precisely what Viking had seen and dismissed as contamination from Earth. The organics had been there all along. Viking had cooked them using a chemical nobody knew was in the dirt. We had been standing on the explanation for 3 decades and reading it wrong. That reframing carried a warning inside it. If perchlorate had been quietly shaping our data since the 1970s, then it was not some rare deposit Phoenix happened to land on top of. It was a feature of the planet itself. The confirmation came from the other side of Mars. When the Curiosity rover landed in Gale Crater in 2012, far to the south, near the equator, thousands of miles from the Phoenix site, it carried an instrument suite called SAM, the Sample Analysis at Mars. As Curiosity drilled into rock after rock and scooped soil after soil, SAM kept finding the same family of chlorine-oxygen compounds in nearly every sample it touched. North Pole, equator, surface dust, drilled bedrock. The salt was everywhere it looked. And from orbit, a chlorine map built earlier by the Mars Odyssey spacecraft showed the same story written across the whole globe. The elements spread so evenly that the only sensible explanation was the dust storms themselves. lifting the fine grains and smearing them pole to pole until no part of the planet was clean. So the picture inverted. The thing we had treated as a local oddity, then as an astrobiology footnote, was in fact a global coating. Every gram of dust that would ride a suit through an airlock, every liter of water a crew would melt from the ground, every shovel of soil a greenhouse would try to grow food in, carried it. The resource the entire settlement plan depended on was preloaded with a chemical we keep behind warning labels at home. To make that concentration tangible, hold a handful of Martian topsoil in your mind. Somewhere between 0.5% and 1% of its weight is perchlorate, the same oxidizer that burns in a road flare. That sounds small, a fraction of a fraction. But the salt is so potent in the body that the perchlorate riding in just a few handfuls of that soil, dissolved into water and swallowed, would be enough to kill a grown adult. The crew would be living and working and sleeping inside a material whose lethal ingredient is not hidden away in trace amounts. It is a measurable percentage of the dirt spread across an entire planet, lying on the floor of every room they would ever manage to build. For 30 years, the question about perchlorate on Mars had been an astrobiology question. Does it help life or hurt it? The discovery, slowly, quietly, replaced that question with a sharper one, and almost nobody was asking it out loud yet. Because if the entire surface is dusted with a compound that, in the right amount, goes hunting for one specific gland in the human body, then it no longer matters very much whether Martian microbes can tolerate it. What matters is what it does to a person who has no way to avoid breathing it, drinking it, and living inside it for years. To answer that, you have to stop looking at the soil and start following the salt into the body, into the lungs first, because that is where it gets in. In 2025, a team of researchers led by Justin Wang at the Keck School of Medicine of the University of Southern California published a long review in the journal GeoHealth, asking a question the early Mars studies had mostly skipped. Not whether the dust was toxic in a beaker, but what it would actually do inside a human being living in it for years. The most important number in their work is a measurement of size. The average grain of Martian dust is about 3 microns across, 3 millionths of a meter. To picture how small that is, a single human hair is around 70 microns wide, so you could lay more than 20 of these dust grains side by side across the width of one hair and still have room to spare. That size is the whole problem. Your airways are not defenseless. They are lined with mucus and tiny beating hairs called cilia that catch incoming particles and sweep them back up and out, the reason a dusty room makes you cough rather than kill you. But that defense has a lower limit. Particles smaller than about 5 microns slip underneath it. They are too fine to be caught and carried back out, so they ride the air all the way down into the deepest pockets of the lung, the alveoli, where your blood meets the atmosphere across a membrane thinner than a soap bubble. Martian dust, at 3 microns, sits comfortably below that line. It is built, by sheer accident of geology, to go deep and stay. And once it settles in that deep tissue, the dust does not just sit there as an inert speck. It begins to dissolve. The perchlorate salt that coats it goes into solution in the warm, wet lining of the lung and crosses into the bloodstream, the same way a tablet dissolves under your tongue. The crew would not need to drink anything or eat anything to start absorbing it. They would only need to breathe the air inside a habitat that the dust had gotten into, which, going by every account from the moon, it absolutely would. We are not guessing about that part. We have the testimony of the only people who have ever worked on the surface of another world. When the Apollo crews climbed back into their landers after walking on the moon, the dust came with them, ground into every fold of their suits, and the moment they took their helmets off, the trouble started. Apollo 17's Harrison Schmitt, a trained geologist and one of the last two men to walk on the moon, breathed it in and was hit with sneezing fits, streaming eyes, and a raw throat. He called it lunar hay fever. Every one of the 12 people who walked on the moon reported some version of it, and for a few of them, the symptoms took days to fade. The dust smelled, they said, like spent gunpowder. It clung to everything, because the airless lunar surface leaves it electrically charged, and no amount of brushing got it off. That was after 3 days. The dust was abrasive enough that, in that short time, it scratched visors and chewed into the outer layers of the Apollo spacesuits. And when researchers later ground up simulated lunar dust and exposed human lung cells to it in the laboratory, the dust killed those cells and damaged their DNA. Now hold the one difference that changes everything. Lunar dust does not contain perchlorate. The moon never brewed it. The moon's dust is merely sharp and fine and toxic to living tissue. Mars takes that same fine, sharp, lung-penetrating dust and laces every grain of it with a thyroid poison. We already know the mechanical half of the danger is real, because it sickened the only humans ever exposed to it after 72 hours. Mars adds a chemical half the moon never had, and the stay is not 3 days. It is years. So the salt gets in. The next question is what it does once it is in the blood, and here the answer becomes unsettlingly specific. Perchlorate does not attack the body at random. It goes after one gland. To understand why, you have to know about a small protein in your cells called the sodium-iodide symporter, often shortened to NIS, which was characterized in detail by the molecular biologist Nancy Carrasco and her colleagues, work she carried into her lab at Yale. The job of this protein is to grab iodide out of your bloodstream and pull it into the cells of your thyroid, the butterfly-shaped gland in your throat. Your thyroid needs that iodide to build its hormones, the chemical messengers that set the pace of nearly everything your body does, from how fast you burn energy to how your heart keeps time. Here is the cruel part. The perchlorate ion happens to be almost exactly the same size and shape as iodide, and it carries the same electrical charge. So when it reaches that little transport protein, the protein cannot tell the difference. It grabs the perchlorate and pulls it in, mistaking the poison for the nutrient. Worse, perchlorate binds to that transporter more eagerly than iodide does. It does not just sneak through the door, it jams it. With perchlorate sitting in the way, the thyroid can no longer pull in the iodide it needs, and the production of its hormones begins to fall. The gland is not destroyed. It is simply starved of its raw material, quietly, while the salt keeps arriving with every breath. In an adult, the early effects of that are not dramatic, which is part of what makes it dangerous. A slowing metabolism, fatigue that does not lift, cold that bites harder than it should, weight that creeps, a mind that fogs. On a planet that is already cold, already exhausting, already strange, the first symptoms of perchlorate poisoning would be almost indistinguishable from the ordinary toll of being on Mars at all. By the time anyone connected the pattern, the crew would have been absorbing the salt for months. And that same transport protein, the one perchlorate jams, does one other thing that turns this from a problem for the crew into a problem for any future they might try to build. Carrasco's work showed that the sodium-iodide symporter is not only in the thyroid, it is in the placenta and in the breast. It is the very channel a mother's body uses to pass iodide to a developing fetus and later to a nursing infant. Block it, and you do not only starve the mother's thyroid, you cut the supply line to a growing brain in the window when that brain needs iodine most. Hold that thought. We will come back to it, because it is the quietest and heaviest part of this whole story. To understand how much weight that one nutrient carries, look at our own history with it. Iodine deficiency, the simple lack of enough iodine in the diet, was for most of human history the leading preventable cause of intellectual disability on Earth. When a developing brain does not get the thyroid hormone it needs, the damage can be permanent, written into a person before they are even born. We mostly solved it with a trick so cheap it is almost invisible. We added a trace of iodine to table salt. That is all it took to protect entire generations. Now picture the opposite move. A planet that does not add iodine but subtracts it, that floods the body with a molecule whose entire effect is to block the one channel that delivers it in exactly the population least able to spare it. And what the thyroid actually controls is what makes a poison aimed at it so much worse than a poison aimed at almost anywhere else. The hormones this gland produces are not a side system. They are closer to the body's master clock. They set your metabolic rate, the speed at which every cell burns fuel. They help regulate body temperature, heart rate, the way you process energy, even mood and the capacity to concentrate. Starve the thyroid slowly, and a person does not collapse. They dim. The cold reaches them more easily on a planet that is already freezing. Their energy drains on a mission that already demands everything. Their thoughts slow and their focus frays in an environment where a lapse in judgment can kill. Hypothyroidism in an adult is a gradual fading of the very faculties a person on Mars cannot afford to lose. And because it comes on so quietly, it would be the easiest thing in the world to blame on the hardship of simply being there. In a child, the stakes are not faded faculties, but a foundation laid wrong. Thyroid hormone helps wire a developing brain and build a growing skeleton. There is a narrow window before birth and in the first months after, when its absence does damage that no later treatment can repair. That is the window Perchlorate threatens by jamming the supply line at exactly the moment it matters most. The salt does not pick a random target. It picks the one gland whose failure echoes through everything else, and it does its quietest, most permanent harm in the smallest, newest bodies. Now, I want to be honest about where the science is solid and where it is still arguing with itself, because the trusted version of this story is not the loudest one. The danger of swallowing perchlorate is well established. So is the danger to a developing fetus, which is why health agencies on Earth set their exposure limits with pregnant women and infants specifically in mind. But the precise risk of breathing fine perchlorate dust day after day for years in the exact way a Mars crew would is less nailed down than you might expect. Studies of factory workers who handle perchlorate showed surprisingly little thyroid disruption from inhalation alone, and some toxicologists argue that a healthy adult can clear modest doses faster than the salt can do lasting harm, since it washes out of the blood in a matter of hours. The honest position is that we do not have a clean human dataset for the Martian scenario because no human has ever lived that scenario. What we have is a known mechanism, a known global contaminant, a known particle size that defeats the lung's defenses, and a timescale measured in years. The pieces are not in doubt. The exact sum is. What is not in any doubt is how cautious we are about this molecule here at home. When a scientific panel set a safe daily limit for perchlorate intake, with pregnant women and infants held foremost in mind, they landed on a figure measured in hundredths of a milligram a day, a vanishingly small amount, and called even that conservative. Set that speck of a safe dose beside a planet whose dust is 0.5% to a full percent perchlorate by weight, whose water can run to millions of parts per billion, whose every exposed surface is dusted with it. The mismatch is almost absurd. On Earth, we treat trace contamination, a few parts in a billion, as a public health problem worth real money to fix. On Mars, it is not a trace, and it is not an accident. It is the ground itself. But there is one historical episode that should make anyone cautious about waving the danger away. In the 1950s, doctors actually used potassium perchlorate as a medicine. It was prescribed to calm overactive thyroids precisely because it is so good at blocking iodide uptake. For a while it worked. Then the reports started coming in. Some patients on the drug developed aplastic anemia, a condition in which the bone marrow stops making blood cells, and for a number of them it was fatal. The body, robbed of new blood, becomes defenseless against infection. There are accounts of patients who, despite every treatment available, slipped away from infections their failing marrow could no longer fight. Perchlorate was quietly pulled as a frontline thyroid drug. We learned on our own population that this molecule has a second and darker mode of harm beyond the thyroid, and we learned it the hard way. And those deaths point to how little perchlorate it takes. The doses that proved fatal in those thyroid patients were under 1 gram a day, taken for months, not a single massive swallow. As a powerful oxidizer, it is dangerous at the acute end too, attacking the blood and the kidneys in large enough amounts. And here is where the Martian water plan, the one I promised we would return to, finally breaks. The salts dissolved in raw water pulled from Martian ground can run so concentrated that a single day's drinking supply, untreated, could carry several grams of perchlorate, many times over the daily amount that has already killed people here on Earth. You would not be sipping mildly tainted water. You would be holding a cup that, taken day after day, would poison the body that drank it. To make it safe, you would have to strip the perchlorate down by a factor of around 100,000 every liter, every day, forever, with equipment light enough to have flown there and reliable enough that a single failure does not poison the crew. And there is a deeper cruelty in where that water comes from, because the salt and the water are not strangers. They are partners. One of the stranger properties of perchlorate is that it is hygroscopic, which means it pulls moisture straight out of the air. And when it dissolves into water, it drops the freezing point so far that the resulting brine stays liquid at temperatures that would lock pure water into ice. On a planet as cold and dry as Mars, that is everything. Scientists studying the dark streaks that creep down certain Martian slopes in the warm season, features called recurring slope lineae, have spent years arguing over whether they are flows of exactly this kind of perchlorate brine, water kept liquid by the very salt that would poison you. The orbiter that found chemical hints near those streaks helped build the case that wherever Mars still holds anything like liquid water near its surface, the perchlorate is part of the reason it is there at all. So the trap tightens one more turn. The salt is not only a contaminant floating in the water you have to remove. In some places, the salt is the only reason the water is liquid enough to find. You cannot cleanly pry the two apart because the chemistry that lets Mars cling to a little moisture is the same chemistry that makes that moisture deadly. The planet does not offer you water with a poison problem. It offers you a poison that, now and then, behaves like water. And the salt does not even travel alone. The same fine dust that carries perchlorate into the lungs is carrying a whole cabinet of other hazards with it. Close to half of Martian dust is silica, the fine crystalline mineral that on Earth scars the lungs of miners and stonecutters into a disease called silicosis. Silicosis has no cure. The scarring is permanent. Once enough of that glassy dust has lodged in the deep tissue, the lung simply loses capacity and never gets it back. Alongside the silica, there is a reactive form of iron oxide ground to a nanoscale fineness that irritates and inflames the tissue it touches. There is gypsum, and there are traces of genuinely toxic metals, chromium and arsenic and cadmium among them, the kind of inventory that would shut down a work site on Earth. Take silicosis on its own for a moment, because it is the clearest warning. It is one of the oldest occupational diseases we know, the affliction of miners and sandblasters and stone carvers, caused by breathing fine crystalline silica until the lung walls itself off in useless scar tissue. There is no treatment that reverses it, no drug, no surgery, no recovery. The only defense humanity has ever found against silicosis is to not breathe the dust in the first place, which is precisely the thing a Mars crew cannot promise. Nearly half of every breath of disturbed Martian dust is this mineral. And the metals are not harmless trace garnish. Some forms of chromium are potent carcinogens. Arsenic and cadmium are poisons in their own right, the sort we monitor carefully in soil and water on Earth. When the researchers who have spent years trying to grow food in Martian soil simulant are asked what worries them about the real thing, they do not soften it. Everything poisonous you can think of in terms of heavy metals, one of them said, is in those soils. So the dust is not a single threat wearing one mask. It is a powder of overlapping poisons, each with its own door into the body, bound together in particles small enough to reach the deepest tissue you have, and breathed by people who cannot stop breathing. The Wang Review made a point about all of this that is easy to miss and important to hold on to. These hazards do not add up. They multiply. A lung already scarred by silica handles perchlorate differently than a healthy one. A body already dosed with radiation from the journey out, its tissue already primed for the kind of scarring that radiation and fine dust both produce, faces a compounded risk rather than a list of separate ones. The crew would not be fighting perchlorate, then silica, then radiation, then cold, one at a time, like levels in a game. They would be fighting all of it at once, in a single body, where each injury makes the others worse. This is the real shape of the threat, and it is why perchlorate is the right name for the whole thing, even though it is not the only poison in the dust. The other hazards are dangerous. Perchlorate is dangerous and everywhere and aimed. It is in the soil you shield with, the water you drink, the dust you cannot keep out, and the air you breathe inside your own home. And of all the things in that cocktail, it is the one that goes hunting for a control system, the gland that governs how your body burns its fuel, regulates its temperature, and builds a brain. The Martian dust is the delivery system. Perchlorate is the payload that reaches for the thermostat. What the mechanism tells us in the end is what kind of death this is. It is not the loud, fast death of a failed seal or a dark dust storm, the kind we built our fears and our films around. It is slow. It is attritional. The planet does not strike the first crew down in a moment. It wears them away, gram by gram, breath by breath, on a time scale long enough that the people living it might mistake their own poisoning for ordinary hardship until the damage is set. And it leaves one question standing that the chemistry alone cannot answer. We can model what years of this would do to a grown crew that arrived healthy. What we cannot model, what we have almost no honest data on at all, is what it would do to someone who never arrived because they were born there. To a child conceived under a salted sky, in a third of Earth's gravity, fed iodide through a channel the planet is busy jamming. That is where the implications stop being about the first crew and start being about whether there can ever be a second generation. Now consider what this means for the idea that has driven the whole dream. Not a visit, a settlement. People who do not come home. Children. Every vision of a permanent Mars, from the boldest private blueprints to the patient ones, eventually arrives at the same milestone. A first child, born on another world. It is the moment a base becomes a home, the line that turns explorers into settlers. And it is the single thing we understand least because it sits at the intersection of two enormous unknowns, and the planet has rigged both of them against us. The first unknown is the gravity. Mars pulls at about 38% of Earth's strength, a little more than a third of the weight you feel right now. We have a great deal of data on what zero gravity does to a grown body, and almost none of it is encouraging. In orbit, astronauts lose bone at a rate of around 1 to 1.5% every month, the skeleton dissolving because nothing is pushing back against it. Muscles waste. The heart, no longer fighting to pump blood uphill, grows lazy and weak. Fluid drifts into the skull and presses on the eyes, reshaping them, blurring vision in ways that do not always recover. That is what we know happens at zero. What we do not know, what we have never had the means to measure, is what happens at a third. Is 38% of a pull enough to tell a growing skeleton which way is down? Enough to build a working heart, a straight spine, a pair of eyes that focus? Nobody can tell you because the experiment has never been run on a human, and there is no way to run it except by living it. And the countermeasures we rely on in orbit may not carry over at all. On the International Space Station, astronauts fight the wasting of weightlessness with hours of daily exercise, strapped into treadmills and resistance machines. And even then, they come home with thinned bones, weakened hearts, and for some, vision that never fully sharpens again. But that whole regimen treats adults who arrived fully grown. It says nothing about a body assembling itself from a single cell. You cannot strap an embryo to a treadmill. You cannot coach a developing skeleton through resistance training in the womb. Whatever a third of Earth's gravity does or fails to do to a growing human, it would do during the one stretch of life we have no way to reach into and correct, and no way to undo once it is done. We have tried to glimpse the answer in animals, and the results refuse to settle into a clean story. Decades ago, two-celled mouse embryos flown in simulated low gravity failed to develop, and for years that was taken as an ominous sign. But more recent work has muddied it. In a study published in 2023, researchers thawed and grew 720 mouse embryos aboard the International Space Station, and most of them progressed from two cells to the blastocyst stage with few obvious defects, suggesting early development can proceed in weightlessness after all. Japan's space agency even built a centrifuge for the station, a system called Mars that can spin small habitats up to Martian gravity to test it directly. We are slowly learning how to ask the question. We have not answered it, and there is a vast distance between an early embryo dividing in a dish and a child carried to term, born, and raised to adulthood under a sky that never gave its ancestors a full Earth's weight. That is the first unknown. The second is the one we have already met. Remember the transport protein from earlier, the sodium-iodide symporter that perchlorate jams. Remember that it is not only in the thyroid, it is the channel a mother's body uses to feed iodide across the placenta to her developing child, and later through milk to her infant, in exactly the window when a brain is laying down its architecture and needs iodine most. So picture the situation honestly. A pregnancy on Mars would unfold in a third of Earth's gravity, an environment we cannot promise a fetus can even build a body in, while the mother breathes a salt that quietly throttles the very supply line her child depends on for normal brain development. Two unknowns, stacked in the most fragile process the human body performs. The first child born on Mars would not be a triumph. It would be an experiment, run on a person who never consented, with a hypothesis we already have reasons to fear. And the cruelty of it is that nothing about that child's risk would announce itself in a dramatic way. There would be no alarm, no breach, no countdown, only the slow accounting of a body trying to assemble itself out of materials a poison mother could not fully provide, on a world that may not pull hard enough to shape it. Step back from the cradle, and the same logic spreads across the entire dream. Look again at the images we tell ourselves about Mars. Greenhouses bright with crops, children in a dome watching a thin sunrise, a town, then a city, then 1 million people living off a planet that finally provides. Now run every one of those images through what we have learned. The crops grow in regolith laced with perchlorate, and plants do not politely leave the salt in the dirt. Many take it up through their roots and gather it in their leaves and stems, which is exactly why leafy greens are the crops most watched for perchlorate contamination here on Earth. A salad grown in untreated Martian soil could carry the salt concentrated in the very part you eat. The children breathe air the dust has gotten into. The city drinks water it has spent enormous energy trying to scrub 100,000-fold, knowing a single failure in that chain poisons everyone downstream. The romance does not survive contact with the chemistry. Every warm image of a Martian home turns out to route directly through the one material that is trying to kill the people in it. We have actually tried the farming, which is what turns this from a worry into a fact. Since 2013, a plant ecologist named Vega Vemelink at Wageningen University in the Netherlands has run a project with the hopeful name Food for Mars and Moon, growing real crops in soil engineered to mimic Martian regolith. The first results, published in 2014, looked genuinely good. His team raised 10 different crops, tomatoes and peas and radishes and rye and rocket among them, and the yield in the Mars-like soil was barely different from ordinary potting compost. In 2016, they even sat down to a dinner of vegetables grown this way. It is about as close as anyone has come to the scene from the film The Martian, the stranded astronaut coaxing potatoes out of alien ground. But read the fine print and the dinner turns uneasy. The researchers did not eat most of what they grew, and they were blunt about why. The simulant carries heavy metals, lead and arsenic and mercury, and a great deal of iron, and if those find their way into the plant, they climb into the parts you would eat. And here is the detail that matters most of all. The simulant does not even contain perchlorate. The laboratory soil is missing the worst ingredient. The real Martian regolith carries the salt that the test dirt lacks, which means every encouraging harvest on Earth has been grown in a cleaner, gentler, more forgiving version of the ground than anything that exists on Mars. Wamelink himself does not pretend otherwise.
The perchlorate, he has said, would have to be removed or eaten away by bacteria before you could safely grow anything at all. And because the radiation pours down through a sky with no shield, the crops would have to be grown underground, under artificial light, in the first place. The greenhouse with the thin sunrise is the wrong picture. The honest picture is a buried room, lit by lamps, growing food in dirt that had to be detoxified with microbes before a single seed went into it. And this forces a harder thought about our place in the cosmos, one that reaches past Mars. We talk about the habitable zone, the band of distance around a star where a planet is neither too hot nor too cold for liquid water. We point our telescopes at distant worlds in that zone and call them potentially habitable, and we let the word do a great deal of quiet work. But Mars sits at the very edge of our own habitable zone, and Mars is a slow poison from pole to pole. Being the right distance from a star, it turns out, tells you almost nothing about whether the ground will let you live. It tells you about temperature. It says nothing about the chemistry waiting in the soil, the radiation pouring from the sky, the gravity that may not be enough to grow a child. The galaxy may be full of worlds in the habitable zone that are, on closer inspection, exactly like this one. Beautiful from a distance, lethal underfoot. Think about what that does to the catalogue of distant hopes we keep. Every few months brings news of another world found in its star's habitable zone, another candidate for a second Earth, and each one arrives as a small lift of possibility. But every one of those worlds is known to us only as a dot of light and a handful of inferred numbers. Its distance, its size, the temperature we calculate. We cannot see its soil. We cannot taste its water or sample its air. We are reading the brochure and skipping the fine print, because the fine print is invisible across the light years. Mars is the one place in that whole catalogue we have actually walked up to and touched, the single world where we got to read the fine print, and the fine print said, poison. It is sobering to wonder how many of those distant, promising dots would tell us the same, if only we could get close enough to scuff the dirt. Maybe that is part of why the sky is so quiet. Not because life is rare, but because the gap between a world that looks livable and a world that actually is may be far wider than a telescope can see. We have only ever stood on two solid surfaces beyond our own, the Moon, and through our machines, Mars. And both of them are coated in fine dust that would scar our lungs and chemistry that would wreck our bodies. 2 for 2. That is a small sample, and I would not build a philosophy on it. But it is not a hopeful sample either. There is a dimension to all of this that the chemistry charts never show, and it belongs to the mind as much as the body. Imagine actually living it. A crew on Mars would be more isolated than any humans in history, farther from rescue than anyone has ever been. Sealed in a shelter they cannot leave without armor, on a surface that is quietly working to take their lungs and their suits apart. The work that justifies their being there is outside, which means going out into the dust again and again, knowing each excursion drags a little more of the poison home. Every cough could be the ordinary dryness of recycled air, or the first scratch of silicosis that will never heal. Every long stretch of fatigue could be the punishing rhythm of the Martian day, or a thyroid going slowly quiet. And no test result, no reassurance, no second opinion from a specialist arrives in less than the better part of an hour. The weight of that, the unbroken vigilance over your own decline, with help a planet away, is its own kind of hazard, and there is no filter for it and no pill. We have rehearsed the isolation, if not the poison. In a facility in Moscow,
a crew of 6 volunteers once sealed themselves into a mock spacecraft for 520 days, a study called Mars 500, simply to learn what that span of confinement does to people. Some of them grew lethargic. Their sleep drifted out of rhythm, their days blurred together, their drive thinned. And that was on Earth, with a door to the outside world a few steps away and not one grain of perchlorate in the air they breathed. The real thing would lay a slow physical poisoning on top of a psychological pressure we already know bends people, and it would do it with none of the quiet escape hatches the rehearsal kept in reserve. This is what makes the slow death so much heavier than the fast ones we feared at the start. A blowout, a failed seal, a sudden storm. These are terrible, but they are over in a moment, and they are nobody's long ordeal. Perchlorate and the dust it rides in on, and the radiation pouring down from overhead offer the opposite of mercy. They offer time. Time to notice. Time to wonder whether the headache means something. Time to watch a crewmate change across the months and not be sure whether you are imagining it. The planet does not ambush you. It accompanies you patiently for years. And perchlorate, remember, is only the quietest of the planet's weapons. Set it aside for a moment. Imagine you solved it completely, scrubbed every cup of water and filtered every breath. The loud killers we met at the start, the ones we set down to follow the salt, are still standing there waiting. And when you look closely at why they are so bad, they turn out to share a single root with the perchlorate, an ancient catastrophe that shaped the whole planet at once. Mars is not shielded. That is the fact under all of it. Earth keeps us alive partly through something we never see and rarely think about. Deep inside our planet, a vast ocean of molten metal churns, and that motion generates a global magnetic field that wraps the entire world in an invisible shell. That shell deflects the constant stream of charged particles the sun throws at us, the solar wind, and it turns aside much of the deadlier radiation from deep space. We live at the bottom of a magnetic harbor, and almost none of us know it is there. Mars has no such harbor. Not anymore. It used to. The crust of Mars still carries faint magnetic stripes, frozen into ancient rock the way a recording is frozen into tape, and they tell us that early in its life, the planet ran a churning metal core of its own and held up a magnetic shield like ours. But Mars is roughly half the size of Earth, and small things cool faster than large ones. Somewhere between about 4.2 billion and 3.7 billion years ago, the Martian core cooled enough that the churning slowed and the dynamo faltered and the global field flickered out. Bruce Jakosky, the scientist who led NASA's MAVEN mission to study exactly this, has placed the turning point at around 4.1 billion years ago. The shield came down, and once it did, the sun got to work. MAVEN, which has been orbiting Mars and measuring its vanishing air since 2014, caught the process still happening. The solar wind reaches the unprotected upper atmosphere and strips it away, atom by atom, into space, and the rate jumps sharply whenever a solar storm rolls through. Over billions of years, this is how a world with rivers and lakes and a sky thick enough to keep them liquid became the freezing, near vacuum we see now, its atmosphere reduced to less than 1% of ours. The planet did not just die, it was scoured. And the same loss of the shield that let the air be stripped away is the reason the radiation now pours straight down onto the surface with almost nothing to stop it. On Earth, the magnetic harbor and the thick atmosphere turn aside the storm. On Mars, the storm lands. By MAVEN's accounting,
Mars has lost something like 2/3 of the atmosphere it was born with, bled out into space across billions of years, and the little that remains is being thinned still. There is no putting it back. The gas is not hiding somewhere on the planet, waiting for us to release it. It is gone, scattered into the solar system, and with it went any chance the world had of holding warmth or pressure or running water on its own. When we picture Mars, we are not looking at a planet that is merely resting between chapters. We are looking at the aftermath of a world that suffocated, slowly, a very long time ago. Which means the radiation is not only a slow statistical tax on the journey out, it is also, on the worst days, a fast and direct threat, and we have a chilling demonstration of how fast. In August of 1972, the Sun let loose one of the most violent storms of the entire space age, a flare so strangely shaped that solar physicists nicknamed it the Seahorse Flare, followed by a swarm of high-energy protons that battered the inner solar system for days. It was powerful enough to set off magnetic sea mines in the water off the coast of Vietnam, and by pure luck of the calendar, it fell in the gap between two Apollo missions. The crew of Apollo 16 had splashed down in April. The crew of Apollo 17 would not launch until December. Had astronauts been in space during those August days, outside the protection of Earth's magnetic harbor, the best estimates say they could have absorbed a dose in the range of 400 rem, enough to cause severe radiation sickness and quite possibly to kill them. A single bad week of weather on the Sun could have ended a crew. On a months-long flight to Mars, and on a surface with no magnetic shield overhead, there is no guarantee the calendar stays kind, and even the ordinary, everyday radiation of deep space, the galactic cosmic rays that never stop, does something to the body we are only beginning to understand. And it is not the cancer we usually worry about. It is the brain. Charles Limoli, a radiation oncologist at the University of California, Irvine, has spent years studying what these particles do to the nervous system. Working at NASA's dedicated Space Radiation Laboratory at Brookhaven National Laboratory, his team exposed mice to the kind of heavy, fast atomic nuclei found in cosmic rays, and then watched their brains. What they found has an unnerving name. Researchers call it space brain. The radiation set off lasting inflammation in the brain and physically stripped down the neurons, cutting the branching structures called dendrites and the tiny spines along them by 30 to 40% in regions tied to reasoning and memory. The animals performed worse on tests of learning. The damage was still there 6 months later. Limoli has said plainly that the particles pass through the ship and through the body, and that there is, in his words, really no escaping them. A crew could arrive at Mars with their judgment and memory already quietly eroded in the exact moment they most need to think clearly, with help 44 minutes away. You might assume the answer is just more shielding, and for one kind of radiation it is. The bursts of particles thrown out by a solar storm, the kind that nearly caught those Apollo crews, are relatively low in energy, and a thick enough wall of water, of rock, of the habitat's own stored supplies, can blunt them. The standard plan is a storm shelter, a heavily shielded room the crew dives into when the sun flares. But galactic cosmic rays are a different animal, and they expose the limit of the whole idea. They are so energetic, moving so close to the speed of light, that ordinary shielding does not stop them. It does something worse. When one of these particles strikes a shield, it shatters atoms in the material and sprays out a shower of secondary particles, so that a thin or moderate shield can leave you facing more radiation than no shield at all. To truly turn aside the cosmic rays, you would need meters of mass wrapped around every space a human occupies, and every ton of that mass has to be flown across the solar system or dug out of the poisoned ground after you land. This is why the honest assessments keep circling back to the same bleak phrase. For the cosmic rays, on the journey out and on the unshielded surface alike, there is no practical place to hide. And the surface is not a passive backdrop to any of this. It fights. Those planet-swallowing dust storms do more than darken the sky and starve the solar panels a habitat would live on. The fine grains, tumbling against each other in the dry air, build up static charge the way a balloon does against your hair, so the dust clings to every surface and crackles against sensitive electronics. The same dust scours like a slow sandblaster. On the moon, 3 days of it ground into the Apollo suits. On Mars, those suits would have to survive years of it, every seam and joint and visor worn down by a powder finer than smoke and edged like broken glass. And all of this plays out in a cold so deep that a torn suit or a stalled machine bleeds its heat into the black sky within minutes on a surface that, remember, lies entirely above the line where the low pressure alone would boil the water in living tissue. Every time the crew stepped outside to do the work they crossed the solar system to do, they would be threading between half a dozen ways to die at once. And they would arrive already diminished because the journey itself extracts a price before the surface ever gets its turn. The crossing to Mars takes roughly 7 months in weightlessness, and we know what that does to a body because we have watched it happen on the space station for decades. Bone thins, muscle wastes, the heart deconditions, and fluid shifts up into the skull. A crew would step out onto the most hostile surface humans have ever faced in the weakest physical condition of their lives, after more than half a year of their own skeletons quietly dissolving, with no easing in, no recovery ward, and no flight home if it went badly. The windows that let you travel between the two planets open only about once every 26 months when the orbits line up. Miss your window and the next one is 2 years away. So once a crew commits to the surface, they are committed completely, with no abort and no early return and no resupply that is not itself a 7-month throw across the dark. And the radiation figures we have, sobering as they already are most likely the gentle version. The doses the Curiosity rover measured were gathered when the sun was near the busy peak of its cycle, a time when the sun's own magnetic churn actually scatters away some of the galactic cosmic rays pouring in from the wider galaxy. When the sun quiets, that flux climbs, and a crew unlucky enough to travel through a solar lull would take more. On top of the cancer risk, the same radiation is tied to cataracts that cloud the eyes, to damage in the heart and blood vessels, and, as we have seen, to the brain itself. And women, for reasons of body mass and tissue, tend to be more vulnerable to a given dose than men. The single number everyone quotes, the dose that pushes a crew past the safety line, is not a worst case. It is closer to a hopeful average. There is one more quiet vulnerability under all of it, and it is the machines. Everything keeping a crew alive on Mars, the power, the air, the water, the warmth, runs through equipment, and the same dust that scars lungs is brutal on hardware. It coats solar panels until they starve, exactly the way it starved the Opportunity rover into its final silence. The perchlorate is corrosive. The fine grit works into moving parts and grinds them down, and it has already been blamed for wear on rover wheels. A settlement is only as alive as its machines, and from the first day, the planet is sanding those machines down with a dust that finds every gap and seal. The crew would spend their years maintaining the very systems that keep them breathing against a steady, planet-wide effort to clog and corrode and bury them. So even the loud killers are not really separate problems. They are facets of one fact. Mars lost its core, then its shield, then its air and its water, billions of years ago. And everything that makes it deadly flows from that single ancient death. The radiation pours down because the shield is gone. The blood boils because the air is gone. And the salt, as we are about to see, piled up because the water that would have washed it away is gone too. Solve the perchlorate, and the unshielded sky is still there. The planet does not offer one way to die that you can fix. It offers a whole condition you would have to live inside. Which brings us back, finally, to the salt and to the obvious objection that everyone raises. If we know it is there, if we have known since 2008, why not simply take it out? Filter the air, wash the soil, clean the water. We are clever. This is what engineers do. It is the right question. And working through it, one honest countermeasure at a time, is how you come to understand that perchlorate is not a problem with a solution, so much as a trap with several doors, each of which opens onto another wall. Start with the air, since breathing is the most constant exposure. The plan is filtration. You run the habitat's air through fine filters, the same idea as a hospital clean room, and you pull the dust out before it reaches anyone's lungs. The trouble is the size we already met. At 3 microns, Martian dust sits right at the hard edge of what filters can catch, which means the filters have to be fine, and fine filters clog. Every gram of dust they trap brings them closer to useless, so you change them constantly. And here is the catch that Julia Cartwright, a space researcher at the University of Leicester, put plainly when this work made the news. You would need a strategy for changing out every filter you breathe through, and you would need to carry an enormous stock of replacements across the solar system to do it. Each filter change is also a moment when the trapped dust can escape back into the cabin. You are not removing the dust so much as fighting a permanent, losing rearguard action against it. With a finite supply of ammunition, you had to fly in from another planet. And the air will never be clean to begin with, because the dust does not respect the wall between outside and inside. Everything we learned on the moon says so. Apollo crews could not keep lunar dust out of their cabins, no matter what they tried. It rode in on suits, packed into seals, hung in the air, and left astronauts coughing with streaming eyes after a few days. Mars dust is finer than lunar dust, and a Mars mission is not a few days. It is years. Every spacewalk, every airlock cycle, every suit brought back through the door drags the planet inside with it. You cannot filter a room. You cannot stop refilling. So filtration leaks. The next door is the soil itself. Clean the dirt before you use it. This one looks promising at first because perchlorate is extremely soluble in water. It practically leaps off the soil grains the moment it gets wet, which is exactly why the Phoenix wet lab found it so easily. So in principle, you wash it out. You flood a batch of regolith with water, let the salt dissolve away, and pour off clean soil to grow your crops or stack on your roof. And yet, the moment you write down what that actually costs, the door closes. Water is the single scarcest, most precious, most fought-over resource on Mars. Washing soil consumes it in bulk, and the dirty water you pour off does not vanish. It becomes a concentrated toxic brine carrying everything you just stripped out, which you now have to store, treat, or dispose of without poisoning anything downstream. You would have to do this for every batch of soil at the scale of farms and habitats, and shielding berms on a planet where you are already rationing every drop. You are not cleaning Mars. You are moving the poison from the dirt into the water, and the water is the thing you are trying to protect. Which brings us to the water directly, because everything keeps collapsing back onto it. Strip the perchlorate out of the water, and you solve the drinking problem at its source. The methods exist on Earth. Specialized resins that grab the perchlorate ion, membranes that filter it, distillation that boils the water away and leaves the salt behind. But perchlorate is a small, stable, stubbornly soluble ion, genuinely hard to remove. And remember the scale of the job. Raw Martian water can carry the salt at concentrations that must be cut by a factor of around 100,000 to be safe to drink. 100,000-fold reduction achieved on every liter, every day, for years, with equipment light enough to have flown there and reliable enough that it never quite fails. The resins saturate and need regenerating or replacing. The membranes foul. Distillation devours energy, and energy on Mars comes from solar panels that a single global dust storm can starve for weeks, the same storms that killed a hardened rover. And a single bad day in that purification chain does not give you slightly worse water. It gives you a cup carrying many times the amount of perchlorate that has already killed people here on Earth. The margin for error is not thin. There is no margin. The system has to work perfectly, forever, or it kills the people relying on it. Fine, says the optimist. Then do not make water on Mars at all. Bring it from Earth. Bring everything from Earth. This is the plan that quietly undoes the entire reason we thought Mars was reachable. Water is heavy, 1 kilogram for every liter, and a human needs several liters a day to drink, with far more for hygiene and food. Run that out for a crew of a few people across a 2.5-year mission, and you are talking about tens of tons of water alone, before food, before air, before fuel, before everything else. Every kilogram of it has to be lifted off Earth, flown across the solar system, and lowered to the Martian surface, and the cost of moving mass that far is staggering. The whole promise of living off the land, the principle Robert Zubrin built his case on, the principle Moxie proved by making oxygen from thin air, was that you would not have to do this. Abandon it, and the economics that made Mars look possible fall apart. And even then, even if you hauled every drop, the dust would still get into the food, the supplies, the surfaces, the wounds. You cannot seal a home for years against a poison ground finer than smoke. Bringing clean water does not help if the planet keeps salting it the moment it is exposed. Even deciding where to land turns into a version of the same trap. The most accessible water ice on Mars sits at the high latitudes, near the poles, which is exactly where the planet is coldest and darkest, where the sun hangs low and the winters are long and solar power is weakest. The places that are warmer and brighter, nearer the equator, where a crew might actually keep their panels fed and their habitat heated, are the places where the easy ice runs thin. So you are forced to choose. Land where the water is and fight the cold and the dark, or land where the light is and fight to find water. And whichever you choose, the perchlorate is already there, because it coats the whole planet evenly, pole to equator, the one variable that does not improve no matter where you set down. There is no good spot. There is only a menu of different hardships served on the same poison plate. There are gentler countermeasures, and they are worth crediting honestly. You can take iodide the way people take potassium-iodide pills after a nuclear accident, flooding the thyroid with so much of the real nutrient that the perchlorate has a harder time elbowing in. That genuinely helps protect the one gland. but it does nothing about the salt rupturing red blood cells at higher doses, nothing about the silica scarring the lungs into a disease that has no cure, nothing about the iron oxide inflaming the tissue, nothing about the developmental window in a child who needed that iodine in the first place. It is a patch on one leak in a hull that is taking water from a dozen places at once. You can build electrostatic devices to shake dust off suits, design ports that let a crew climb into a suit from inside the habitat without ever bringing it through the cabin. These help. They do not win. Over a long enough mission, on a planet this dusty, the dust always finds the way in, and the crew has to go outside anyway, because going outside is the entire point of being there. Step back far enough, and the real shape of the thing appears. These are not independent problems waiting for independent fixes. They are a single trap that tightens whichever way you push. Wash the soil and you spend the water. Purify the water and you spend the energy. Skip both and haul supplies from Earth, and you break the mass budget that made the journey thinkable. Filter the air and you burn through a finite stock of filters, fighting a tide that never stops coming in. Every door out of the perchlorate problem opens onto another scarcity, and the scarcities are connected, so closing one tends to open another. The contamination is not a stain on the resource base. It is woven into the resource base. The water, the soil, the dust, the air, the food, all the things a settlement must live on, are the same things carrying the poison, and you cannot separate the gift from the threat by any mechanical means we have been able to design. And that, finally, is what points toward the one approach that might not be doomed. If you cannot filter the salt out, or wash it out, or boil it out, or outrun it by importing everything, then the only path left is stranger and older than any machine. You do not remove the perchlorate. You convince something to eat it. And the moment you start seriously planning to do that, the salt stops being only a poison and becomes, of all things, the most useful chemical on the planet. Here is the part almost no popular telling of the Mars story ever reaches. The reason perchlorate is so dangerous is the exact same reason it is so valuable, and the two cannot be separated. Look at what the molecule is actually made of. One chlorine atom bound to 4 atoms of oxygen. By weight, perchlorate is nearly 2/3 oxygen, and that oxygen is held in a tense, eager arrangement, ready to be given up. That is precisely what makes it a vicious oxidizer, the property that lets it burn rocket fuel and rupture red blood cells. It wants to shed its oxygen, and on a planet whose air is almost unbreathable, whose entire economy of survival comes down to where you can find oxygen to breathe and oxygen to burn for fuel, a substance that is 2/3 oxygen by weight, lying loose in the dirt across the entire globe, is not waste. It is the richest oxygen mine on Mars, scattered like dust because it is dust. The trick is getting the oxygen out without it getting into you first, and the most elegant idea for that does not involve a machine at all. It involves life. Perchlorate-reducing bacteria are a real and ordinary thing on Earth. Whole families of microbes breathe perchlorate the way you breathe oxygen, using it to run their metabolism, and the chemistry of how they do it is almost too convenient to believe. The bacteria strip the oxygens off the perchlorate one stage at a time, and at the critical step, an enzyme with the wonderful name chlorite dismutase takes the leftover fragment and splits it cleanly into 2 products. One is chloride, which is the harmless half of ordinary table salt. The other is molecular oxygen, breathable oxygen. The microbe eats the poison and exhales the thing you need most.
And these are not rare or delicate creatures. They live in soils and sediments and wastewater all over Earth, and we already put them to work in treatment plants that scrub perchlorate out of contaminated groundwater, the same contamination we created ourselves. The arithmetic is genuinely appealing. Because perchlorate is nearly 2/3 oxygen by weight, a settlement that processed its soil this way would be releasing a real and useful stream of breathable gas as a byproduct of making the ground safe to touch. One step, two gifts. Clean dirt to grow in, and oxygen to breathe, drawn from a colony of microbes that asks for little more than the poison itself as a meal. Of every plan we have for dealing with perchlorate, this is the only one that reads less like fighting Mars and more like quietly persuading it. This is not a fringe idea.
Back in 2013, in the same body of work that flagged perchlorate as a hazard to astronauts, Alfonso Davila and Chris McKay and their colleagues proposed exactly this. Use concentrated extracts of these natural enzymes or the organisms themselves to break the perchlorate down in Martian soil cheaply, with little energy, and harvest the oxygen the reaction throws off. In their accounting, the same process that scrubs a batch of dirt clean enough to farm in could also help supply a crew with air. The poison detoxifies itself and pays you in oxygen for the trouble. Of every plan to deal with perchlorate, this is the only one that does not just trade one scarcity for another. It turns the threat into the asset. The thing most likely to kill the first settlers becomes, with the help of a microbe, the thing that lets them breathe. None of it would be quick, and none of it would be small. Making even a single habitat's worth of soil and water safe means working through tons of regolith, and to picture doing it across the acreage a self-sufficient settlement would need is to picture an industrial biological effort sustained for years, perhaps generations. You do not detoxify a planet in a season, and every step of it would be permanent. Once you have seeded Martian ground with living Earth organisms and let them spread through the dust and the brine and the buried ice, there is no recall, no undo, no clean planet to return to. The choice to live on Mars by this route is, in the very same motion, a choice to change Mars forever, before we have finished asking what was there to begin with. And that is where the story turns its last and strangest corner. Because to do this, you have to bring Earth life to Mars and let it loose in the ground. Think about what that means against everything we have promised for the last half-century. Since the Outer Space Treaty of 1967, the nations that explore space have been bound by a principle called planetary protection. We do not contaminate other worlds with our own organisms. We sterilize our spacecraft. We plan their deaths with care. We have deliberately destroyed working machines rather than risk a single Earth microbe reaching a place where it might take hold or ruin the search for native life. The entire scientific reason to go to Mars in the first place, the question that sent Phoenix and Curiosity and every lander before them, was whether life ever arose there independently, whether we are alone or merely the first of two. That question only has an answer for as long as Mars stays clean. The only realistic plan to make Mars survivable, then, requires doing the precise thing we have spent decades swearing never to do. To detoxify the soil at the scale a settlement needs, you would have to seed an entire planet with terrestrial bacteria, deliberately, irreversibly, releasing Earth life into Martian ground until it spreads through the dust and the brine and the buried ice. The first permanent human foothold on Mars might have to begin with an act of biological contamination so thorough it can never be taken back. And here, the irony closes like a hand. We came to Mars to find out whether it was ever alive. To live there ourselves, we would have to fill its soil with our own life,
smearing our microbes across the one record we were trying to read, erasing the answer in the act of moving in. The poison forces a choice between two things we want and cannot have together. We can keep Mars pristine and unanswered, a closed book about whether we are alone, or we can make it habitable, and in doing so guarantee that we will never cleanly know what was there before us, because by then it will be partly us. Perchlorate, the salt we dismissed in 2008 as neither good nor bad for life, turns out to sit precisely on the seam between those two futures. There is a deeper layer still, and it is the one that reframes the whole planet. Why is Mars so saturated with this stuff in the first place? Why is the dirt of an entire world soaked in an oxidizer that on Earth is rare enough that we mostly only find it where we made it ourselves? The best current thinking is that Mars manufactures perchlorate in its own thin sky. High in the atmosphere, ultraviolet light from the sun, unfiltered because Mars has no protective ozone layer, drives a slow chemistry that takes ordinary chlorine and builds it up, oxygen by oxygen, into perchlorate, which then drifts down and settles into the soil. On Earth, this kind of thing happens too, in tiny amounts. But on Earth, it does not last. Rain dissolves it and carries it away. Rivers flush it. Microbes in the soil, the same perchlorate-eating bacteria, consume it for energy. Our planet is constantly scrubbing itself clean, with water and with life. Mars has neither. Remember the ancient death of its core, the moment the shield came down and the sun stripped away the air and the water with it. No rain has fallen to wash the salt out since. No global river has flushed it. No living thing has eaten it. So it simply accumulates, century upon century, eon upon eon, with nothing to ever take it back out. We can see a faint echo of this on our own planet, in the one place dry enough to behave a little like Mars. The Atacama Desert in northern Chile is the oldest and driest desert on Earth, so starved of rain that parts of it have gone decades at a stretch without a real downpour, its soil salty and oxidizing, its sunlight coming down nearly unfiltered. And in the Atacama, natural perchlorate accumulates in the ground, the closest match anywhere on Earth to the levels the Phoenix lander measured on Mars. It builds up there for exactly the same reason it builds up on Mars. With no rain to wash it away and almost no life to consume it, the salt the sky slowly manufactures simply stays. Scientists study the Atacama precisely because it is the nearest thing we have to standing on the red planet. It is, in a small way, a preview of what happens to any world once you take away the water and the living things that keep a planet scrubbed clean. The Atacama is what a sliver of Earth looks like when it begins, just barely, to resemble a dead world. Sit with what that implies, because it inverts the usual story we tell about Mars. We think of Mars as a dead world, and we say it the way you would describe an empty room, as if dead means harmless, neutral, waiting. But the soil is poisonous precisely because the planet is dead. The perchlorate piled up over billions of years, exactly because the things that would have cleaned it, flowing water and living cells, went away or never came. The hostility is not separate from the deadness. It is the deadness, given enough time to concentrate. Mars is not a blank page waiting for us. It is a planet that has spent 4 billion years, undisturbed, brewing a chemistry that has no use for us at all. There is one grand answer that people reach for at this point, and it deserves a hearing. Because if it worked, it would sweep the whole problem away. Terraforming. Do not fight the planet patch by patch.
remake it, thicken the atmosphere, warm the surface. Let liquid water run again and turn Mars into a younger cousin of Earth, where crops grow in open fields and the dust settles under rain. It is the oldest dream in the literature, and for a long time it lived comfortably in the space where nobody had done the arithmetic. In 2018, 2 scientists did the arithmetic. Bruce Jakosky, the same researcher who led the MAVEN mission, and Christopher Edwards of Northern Arizona University published a study in Nature Astronomy with a deflating title, An Inventory of the Carbon Dioxide Available for Terraforming Mars. They went looking, using 2 decades of spacecraft data, for all the carbon dioxide still locked in the planet's ice and rocks and soil, the gas you would have to release to thicken the air and warm the world. And they found that it is simply not there. Even if you could bake out every accessible molecule of it, from the polar caps, from the minerals, from the dust, you would not come close to the pressure needed to make the surface livable or warm enough to keep water liquid. Most of the carbon that once gave Mars a real atmosphere was stripped into space billions of years ago when the shield came down, and it is gone for good. Their conclusion was flat and final. Terraforming Mars is not possible with present-day technology or with anything close to it. And notice what that study does not even bother to count, because it does not have to. Suppose you could thicken the air somehow. You would still be standing on ground soaked in perchlorate. You would still be under a sky with no magnetic shield, taking the full radiation of deep space. Terraforming, even in the fantasy where it succeeds, only touches the temperature and the pressure. It does nothing about the salt and nothing about the missing shield. You would have given Mars a breathable sky and left it a poisoned, irradiated floor. The grand answer does not just fail on the arithmetic. It would not even solve the problem we have spent this whole journey describing, if by some miracle it worked. And there is a final, quiet finding that makes the surface stranger than merely toxic. In 2017, researchers Jennifer Wadsworth and Charles Cockle, working in Edinburgh, took perchlorate of the kind found on Mars and exposed it to the same ultraviolet light that bathes the Martian surface. The salt did not just sit there as a slow poison. Activated by the UV, it became actively bactericidal, killing bacteria far faster than the salt alone could. The Martian surface, in other words, is not passively inhospitable. Under that unfiltered sunlight, the perchlorate-laced dust appears to be something close to self-sterilizing, a thin top layer that destroys cells on contact. Whatever you set down on the open surface of Mars, the planet starts taking apart. This is why the search for life on Mars has quietly moved downward. If the surface is an organics-destroying, self-sterilizing layer soaked in a salt that the unfiltered sunlight turns actively lethal to cells, then any life the planet might still hold, or any trace of the life it may once have held, is not going to be sitting on top where a camera can find it. It will be meters down, beneath the reach of the radiation and the reactive chemistry, in the dark and the cold. Perchlorate did not only complicate our plans to live on Mars, it buried the answer to the oldest question we carried there, the question of whether we are alone, pushing it down under a poisoned crust we would have to dig through, carefully and without contaminating it, to ever reach. The same chemistry that threatens the first settlers is the chemistry standing between us and knowing whether anything was ever alive on that world at all. We have even managed to make this exact molecule a problem for ourselves at home, which is its own dark joke. Perchlorate turned up in the Colorado River in 1997 and across great stretches of American groundwater since, leached from the very industry of building rockets and the propellants and flares that go with reaching for space. We regulate it in our own drinking water at the level of a few parts in a billion and spend real money cleaning it up, often using those same perchlorate-eating bacteria to do the work. The chemical we would have to conquer to live on Mars is one we have been spreading across our own planet in the act of trying to leave it. We did not need to fly to another world to meet perchlorate. We have been making our own, and the irony goes one turn deeper than that. Perchlorate is what we burn to leave. It is the oxidizer packed into the solid rocket boosters that have lifted so many missions off the launch pad, the chemical that gives the fire its push. We use it to climb out of Earth's gravity and reach for other worlds. And the first solid world we would try to settle, the one we have spent this whole journey on, turns out to be dusted from pole to pole with the very same molecule. We light it to escape, and it is waiting for us when we arrive. There is something almost mythic in that. The substance of our leaving and the substance of the place we land are one and the same. So here is the overlooked truth that completes the thing we came here to understand. The substance most likely to kill the first humans on Mars is not some exotic alien hazard. It is the planet's oxygen, locked in a form that hunts the body. It is the keeper of what little liquid water Mars still allows. It is the residue of 4 billion years of a world cleaning itself of nothing. And it is the seam between staying alive and keeping the deepest question we ever asked about Mars open. To live there, we would have to defeat the one chemistry that makes Mars what it is. And we would have to do it by filling the planet with ourselves. Go back to where we started. You already knew how Mars was supposed to kill you. The cold, the vacuum, the radiation, the storm. A list 70 years long, and beside every item on it, an engineer's note, confident and reasonable, hard, but solvable. That was the frame we walked in with. Mars as a frontier, a hard country, a problem with a diagram on the far side of it. Everything we have followed since dissolves that frame, slowly, the way the dust dissolves in the lander's little cup of water, because the thing most likely to undo the first people who try to live there is not a force on that list. It is not something you shield against or pressurize away or wait out behind a wall. It is a chemistry the planet has been perfecting for 4 billion years with no one to perfect it for. That is the reframe worth carrying out of all this. Mars is not a frontier waiting for us. A frontier implies a far edge of something that is otherwise ours, a place we are meant to reach. Mars was never meant for anything. It is not ours to inherit, and it is not a second Earth held in reserve. It is an experiment that has been running undisturbed since before the first cell appeared in Earth's oceans. The ultraviolet light has been building the salt in the sky and laying it down in the soil for longer than life has existed anywhere we know of. The cold has been pulling the heat out of the ground every night for a span of time the mind cannot hold. None of it was set up to stop us. The planet does not know we are coming. It has simply been doing this, alone, for 4 billion years, and we would be the one reagent it has never been tested against. We keep describing Mars as dead, as if dead meant safe. We had it backward. We were not looking at a quiet room. We were looking at the patient chemistry of a world that has had no use for us or for anyone since the universe was young. And the salt sits at the center of it, perchlorate. When it first came up in that first cold cup of Martian water in 2008, it was almost nothing, a curiosity, neither good nor bad for life, the scientists said, and moved on. We have spent this whole journey watching that single word gather weight. It is the poison in the lungs and the jam in the thyroid, and the thing that crosses into a child who was never asked. It is the oxygen we would need to breathe and the water we would need to drink, both held in a form that fights us. It is what a world becomes when nothing has cleaned it for 4 billion years. And it is the line between staying alive there and ever knowing what came before us. The same word, meaning all of that now. That is what the planet had waiting in the dirt the entire time. And here is the thing I keep coming back to. We will almost certainly go anyway. Not because Mars wants us. It does not want anything. Not because the chemistry will relent, because it will not. We will go because we are the kind of creature that walks toward the thing that might unmake it, that has always walked out onto the thin ice and the high ridge and the open water, that cannot quite leave a far light alone. Some of us will stand on that red ground. Some will try to stay, and the planet will meet them the way it meets everything, without malice and without mercy, with the same slow chemistry it has been running since before we were anything at all. The first of them will not get to learn the planet the gentle way, from a distance, the way we have learned it tonight. They will learn it the way we have always learned the hardest things, in their own bodies, in real time, with help a planet away. The salt in the soil will not be a fact in a study to them. It will be a cough that does not quite clear, an evening that feels colder than it should, a quiet worry kept to themselves. Whatever we manage to write down now, in the calm of all this distance, they will be the ones who live it in the particular. Maybe that is not a reason to despair. Maybe it is only the truest measure of what it would cost. To live on Mars would not be to tame a frontier. It would be to walk into an experiment 4 billion years in the running and offer ourselves as the variable, knowing the planet has no stake in how it turns out. There is something clarifying in that, once the romance burns off. It asks us to want it honestly, with our eyes open to the salt in the soil, instead of the way we have wanted it so far, with our eyes on a dream that rooted straight through the poison and never noticed. For now, the experiment runs on without us. Somewhere on the night side of Mars, the temperature is falling past 100 below, the way it has every night for longer than there have been eyes to see it. A thin wind is moving the dust, lifting the fine grains a little and letting them settle. The same grains that carry the salt. The same salt that is 2/3 oxygen and will not give it up. No one is breathing there. No filter is failing. No thyroid is starving. No child is being asked to assemble itself out of materials a poisoned world withholds. There is only the dust and the cold and the slow, patient chemistry going on in the dark exactly as it always has. The planet is not waiting for us. It is simply there, red and quiet, and 4 billion years into a reaction it will finish with or without us, while the dust drifts down through the thin air and comes to rest, grain by grain, over a ground that has never once needed us to be alive.